Hi, welcome to my fourth lecture on the series of Chemistry 111. So far in lecture number 1 we covered the SI unit and dimension analysis. Lecture number 2 we talked about scientific notations, significant figures and rounding. Third lecture we talked about the components of matter, atomic structure, isotopes. And today it will be a short lecture on basically laws of matter and Dalton's atomic theory. There are three laws that govern matter as outlined in front of you. First law is the law of conservation of matter. Second is law of definite composition or definite proportions. And third law is law of multiple proportions. So first law, the law of conservation of matter, it can be stated in one of the two ways. The first way of stating it would be that matter can neither be created nor destroyed. Or, in other words, the total mass of substances in a chemical reaction does not change, meaning the sum of the masses of reactants will be equal to the sum of the masses of the product. So let's take an example of a chemical reaction shown in front of you. Glucose, which is C6H12O6, undergoes combustion, in other words, reacts with oxygen, to give you carbon dioxide and water. And 1 mole of glucose, and we will learn it in future lectures, is equal to 180 grams of glucose. So 180 grams of glucose plus 192 grams of oxygen react to give 264 grams of carbon dioxide and 108 grams of water. So if you sum the reactants together, 180 plus 192 is 372 grams of the reactant, and if you sum the products together, 264 plus 108 will also be 372 grams of the product. So in short, the sum of the reactants is equal to sum of the product. That means matter is neither created nor destroyed. We do know that there is little bit more detail to the law of conservation of matter, because Albert Einstein's work did show that mass may not remain constant in reactions, and some of mass would be converted to energy. But the difference is too small to be measured in regular chemical reactions, and therefore we can confidently say that in regular chemical reactions, mass is conserved. We will see in future that in nuclear reactions, the energy changes are so large that mass changes are easy to measure. So there will be changes in mass in nuclear reactions, unlike in regular chemical reactions. The second law is law of definite composition, and it can be stated in several ways. One of the things to understand is this law applies only when you're talking about a single compound. So you're talking about a single compound, and when you're talking about single compound, that compound is made up of 2 or more elements. So these elements are the components of that single compound, and these elements will always combine in a definite proportion by their masses. So the elements combine in a definite proportion by their masses to form that particular compound. Okay, so let's take an example. Say water. Water has 2 parts by weight of hydrogen and 1 part by weight of oxygen. Now, whether you have water from any source, whether water on Earth or you found water on Moon or on Mars, anywhere you found, till the time you have the same compound water, it will always contain hydrogen and oxygen in 2:1 ratio. So that is the meaning of law of definite proportion, that whenever using the word law of definite proportion, you're talking about a single compound, and you're saying that the elements that make up that compound will always be combining in the same proportion. Okay. So they often talk about mass fraction and mass percent. Mass fraction is the mass of that element divided by the mass of the compound, meaning how much of the mass of the compound is contributed by that element. So let's take the example of finding mass fraction of sodium in sodium chloride. We know that 1 mole, and again the concept of mole will be clarified later, but for now just accept this, that 1 mole of sodium chloride that gives 1 mole of sodium Na plus ion and 1 mole of chloride ion. We know that 1 mole of sodium chloride, which is salt, that would be sum of the atomic weights of sodium and chloride, and if you combine the atomic weights of these two, it will be 58.44 atomic mass unit. And we know that 1 mole of sodium would weigh the atomic weight of sodium expressed in grams, which is 22.99 atomic mass unit. And therefore, the mass fraction of sodium in sodium chloride will be equal to, what is the mass of sodium? 22.99 AMU. And what is the mass of sodium chloride? Which is 58.44 AMU. Now this turns out to be 0.3934. So that is the mass fraction, but we often express that as percentage and call it mass percent. So mass percent or mass fraction percent for sodium in sodium chloride will be the mass fraction multiplied by 100, so that will turn out to be 39.34%. So let's see an important concept between mass fraction and the mass of an element. Let's take this example that I've noted in front of you. I took 1 mole of sodium chloride, which is 58.44 grams, and compared that with 2 moles of sodium chloride, which is 116.88 grams. If you calculate the mass percent of sodium in sodium chloride, that is mass of the sodium upon mass of sodium chloride multiplied by 100 if you want to take a percentage. The mass of sodium, as I said, 1 mole of sodium chloride gives 1 mole of sodium, and every mole of sodium weighs roughly 22.99 or 23 grams, divided by the 58.44 grams, which is the weight of the compound. And if you multiply that by 100 to get percentage, you get 39.34%. And that is the mass percentage of sodium in 1 mole of sodium chloride. Let's see what is the mass percentage of sodium in 2 moles of sodium chloride. Again, the formula is the same. It is mass of sodium, and in this case the mass of sodium is 2 times the mass of 1 sodium, because 2 moles of sodium chloride, 2 moles of sodium chloride will give you 2 moles of sodium and 2 moles of chloride. So 2 multiplied by the weight of 1 mole of sodium is 22.9, divided by the total weight of the compound, which is 116.88. And the way we got that is 1 mole of the sodium chloride compound weighs 58.44 grams, so 2 will weigh twice that. And we take a percentage of that, we get the same thing. So what we gather from this is, irrespective of how many irrespective of the weight of the compound, always the mass fraction of the element, which is a component of the compound, will always remain the same. So mass percentage will remain the same. However, let's see the mass. The mass of the element will depend upon the mass of the compound, because you multiply the mass fraction with the mass of the compound to get actually the mass of the element, because mass fraction is nothing but mass of the element upon compound. So if I write mass fraction as mass of element divided by mass of compound, and of course I have to multiply that by the mass of the compound, then these two will get cancelled and you will be left behind with mass of the element. So therefore mass of any of the element consisting which is a component of the compound will be mass fraction of that element multiplied by the mass of the compound. In our case, the mass fraction was 0.3934, and multiplied by the mass of the compound was 58.44, giving you 22.9 grams of sodium in the first case. In the second case, mass of sodium, again the same formula, mass fraction of sodium multiplied by the mass of the compound, same logic we talked about. Mass of element upon mass of compound is the mass fraction, and when you multiply that with mass of compound, the mass of compounds cancel and you are left with mass of the element. So again, the mass fraction is the same, 0.3934 in both the cases. But the mass of the compound in the first case was 58.44, in the second case is twice that, 116.88, and therefore the mass of sodium in the second case is 45.98. So what you notice is, although the mass percentage is the same, so mass percentage will remain the same irrespective of the weight of the compound. But the mass of the element will depend upon the weight of the compound. So that's an important concept to keep in mind, and they often ask this in multiple choice question. So I will write here that mass fraction or mass percent of each element in a compound is fixed. And this is because if the mass fraction changes, the compound will change. Okay. However, the actual mass of the element will depend upon the mass of the compound. This is the important concept to keep in mind. They often ask you in MCQs that mass fraction is independent. It will always be fixed for a compound, but the actual mass of the element will depend upon the mass of the compound. Okay? So let's take the example of calculating the mass ratio of carbon to hydrogen in C2H2. So this is a question asked in. So first of all, you used to say, okay, we have been given 1 mole of C2H2. So 1 mole of C2H2, how much does it weigh? We said in the previous video, the molecular weight is sum of the atomic weights. So here there are 2 moles of carbon atoms. So 2 into each mole of carbon is 12.01 grams. You can refer to the periodic table and see the atomic mass of carbon. So that's what it is. Plus 2 moles of hydrogen, and each mole of hydrogen weighs 1.008 grams. So the total weight of 1 mole of C2H2 is 26.04 grams. Then we find the mass fraction for carbon, which is 2 carbon atoms. So 2 into each carbon atom has atomic weight of 12.01 divided by the weight of the compound 26.04, and that is 0.9224. Same way, the mass fraction for hydrogen is how many hydrogen atoms are there in the compound. There are 2, and therefore 2 into 1.008, which is the weight of each hydrogen atom, divided by 26.04, which is the weight of the compound, and that mass fraction is 0.07742. Therefore, when you have to find the ratio of carbon to hydrogen, you just take those two ratios, 0.9224 divided by 0.0774, which turns out to be 11.91:1, or approximately 12:1. So now we come to the third law, law of multiple proportions. The first thing to understand in law of multiple proportion is we think about this law only when we are dealing with 2 or more compounds. So you are dealing with 2 or more compounds. Unlike the law of definite proportion or definite composition, where you dealt with only one compound, here we are dealing with 2 or more compounds of the same elements. Okay, so say for example you have 2 elements, element A and element B. So we have 2 elements. These 2 elements can combine to form, say, a compound 1. They can also combine in different proportion to form compound 2. Now, of course, if compound 1 and compound 2 are identical, that means they are the same compound, then you're talking about the second law, which is law of definite proportion or fixed composition, where the ratio of A to B in both the compounds will be the same. But because the ratio of A to B in compound 1 is not equal to the ratio of A to B in compound 2, these two compounds are different compounds. Okay, let's say that in compound 1, A contributes say 60% to the weight of the compound. and B contributes 40% to the weight of the compound. And therefore, we can say if I take a ratio of A to B, which will be 60% upon 40%, it will turn out to be 6 by 4 or 3 by 2 or 1.5. What this means is, for every 1 mole of B, there is 1.5 mole of A, because we have A to B and we got the ratio as 1.5 by and denominator is 1. So 1.5 is A and denominator is 1B. So for every 1 of B you have 1.5 A. So that's what is in compound 1. Let's say in compound 2. In compound 2, if it follows the law of multiple proportion, then I'm going to work it in reverse manner, that you will have, if you keep B in this case as 1 mole, so if we keep B constant, for every 1 mole of B, there will be X into 1.5 mole of A, meaning if two elements combine to form two different compounds, and if we have one of the elements mass fixed, then the other element that is remaining will be in some multiple, simple whole ratio multiple. Okay, so if I say that in this case, say A, or rather say if I say B contributes, say, 20% of compound 2, how much of A is that? So what you would say is that it will be a multiple. Now we don't know how much of A, but let's say we give you an example, actual example, where I would say say A is therefore 80% of compound 2. So now here, if you take the ratio of A to B, you will get 80% upon 40% or 2, meaning 2 to 1, meaning for every 1 of B you have 2 of A. Now if you compare, 1 mole of B had 1.5 mole of A, 1 mole of B here has 2, and if you take the ratio of these two, that means the ratio of B in compound 1, which is ratio of A in compound 1 is 1.5. We are taking 1 mole of compound B in both the cases. So A in the first case was 1.5, A in the second case was 2. And if you take the ratio of these two, then 1.5 to 2, 15 by 20, and this does not turn out to be a whole number ratio, because if you divide the two, you get 0.075, which is in decimal, and therefore that, if this is true, this disobeys the law of multiple proportion. Okay, so I hope I clarified the law of multiple proportion, that simply stated law of multiple proportion will only apply for compounds if there are two or more compounds of the same elements, and if the elements are the same in both the compounds, then if you keep the mass of one of that element constant, then the other element, remaining element which is there in each of those compound, their ratio should be in a simple whole number ratio. Okay, that is law of multiple proportion. So in this case, if I want to have this compound to obey the law of multiple proportion, I would say B contributes 25% to the weight of compound 2 and A contributes 75% to the weight of compound 2. In that case, if you take the ratio of A to B, you will get 75 by 25 or 3, meaning for every one part of B there is 3 part of A. So now when you set up this thing that okay, now we will fix the B in both the compounds, so 1 part of B in compound 1, the A part is how much, and in compound 2 the A part is how much. In compound 1, for every 1 part of B you have 1.5, and in compound 2 for every 1 part of B I have 3 parts of A, and therefore now if I take the ratio 3 by 1.5 is 2, and this will obey the law of multiple proportion. So Dalton's atomic theory, there are basically 4 postulates for Dalton's atomic theory. The first postulate is that all matter consists of tiny indivisible particles called atoms, and these atoms cannot be created or destroyed. So this is consistent with the law of conservation of matter, that atoms cannot be created or destroyed. We know now that atoms are not the tiniest particle, but they can be further subdivided into subatomic particles. The second postulate for Dalton's atomic theory is that atoms of one element cannot be converted into atoms of another element. Although the atoms can combine to form a compound, but one element atom cannot be converted to another element. This of course is again consistent with law of conservation of matter. The third postulate is atoms of the same element are identical with respect to their masses and properties, and atoms of different element will have different properties and masses. Those of course are consistent with the law of definite composition and law of multiple proportion. Same thing for fourth postulate, which is saying that compounds are formed when atoms of different elements combine, and when they combine in definite proportions, in specific ratios. So this is again consistent with law of definite composition and multiple proportions. So we will stop here for this video. The next video will be a detailed video on periodic table, and we'll see you there.